Hey everybody, welcome to another Bill Sky the Assembly Guy, and what we're going to do today is talk about variables, talk about data sizes of integer data types. We might even get into some strings. I don't know yet, but let's take a look, and we're going to do some programming in this one. We're going to do it in Linux and Windows, so it should be a lot of fun. Let's get started. Bits, bytes, and words. Why did I title this or entitle this way? Is because assembly language doesn't have data types. It has data sizes. So like in other languages like C or C++, you specify an integer, you specify a char, you specify a string. There is no such thing as that in assembly language. In assembly language, what you have is you have data sizes. Everything starts as a byte, goes all the way up to a T byte, possibly even larger, but they're just sizes. They're not data types. And you, the programmer, have to keep track of what the data type is that you want that size or you want that memory area to look like. So let's first of all take a look at positive unsigned integers. So the smallest unsigned integer is really a bit. You either have a 0 or you have a 1. Now you can access a single bit in assembly language, but normally what you do is you access bytes and bigger. Now bits can be used to tell whether or not a device's headlights are on or whether their arm is up if it's a robot. So we're going to get into that when we get into shifts and bit masks. But really what you're going to be dealing with the most is bytes and larger. And that's what we're talking about. The next size is a byte. A byte's minimum value is 0. Its maximum value is 255. The maximum value is accomplished by turning on all the bits in that byte. And again, a byte is 8 bits. The next one above that is a word. A word is 2 bytes. And the minimum value is 0. The maximum value is 65,535 or 64K, which is 64 times 1024. Again, we're talking about unsigned, so they will always be positive, 0 to 65,535. That's 16 bits all turned on. The next one is the double word, and the double word is 4 bytes, 32 bits, and it goes anywhere from 0 to 4,294, blah, 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 and that's basically 4 gig. So the larger the word size, the larger the data size you're dealing with, the larger the value can be. Also, if the CPU is a 32-bit CPU, it can only address 4,294,967,295 memory addresses because that's the largest number that you can store in a 32-bit CPU. However, a 64-bit CPU uses quad words, and a quad word is 8 bytes, 64 bits, and look at the size of that number. I don't even know, was that a xenobyte, 18 trillion, or is that quadrillion? You can do the math for me, but it's absolutely huge. 0 to 18, 446, 744, 07, it's crazy. So I believe that's 18 terabytes. Or no, it's not. It's xenobytes. It's just huge. It's just really big. In fact, I've read that a 64-bit CPU has a larger number than the total number of protons in the visible universe. It's absolutely crazy. Now, these sizes are the sizes you can use. For instance, you can use a single byte. You can use 2 bytes, which is a word. You can use 4 bytes, which is a double word. You can use 8 bytes, which is a quad word, but you really can't use anything in between. I mean, you can, but it gets quite involved, and I'm not sure why you'd want to do that. And what I mean by that is that between words and double words, a word is 2, a double word is 4, you really can't use 3 as a single piece of data, 3 bytes. So it's either 1, 2, 4, 8, and so forth, powers of 2. It's actually, you might be asking, how did I know what the minimum value and maximum value was of these sizes? And one of the ways to do that is, it's very easy to calculate it. Just take 2, raise it to the power of the number of bits, and then subtract 1. So, for instance, 2 to the 64, or a quad word, is 64 bits. So we take 2 to the 64 minus 1, and we get that huge number. And you can do that for any data type. You can use it for a byte, which would be 2 to the 8 minus 1. A word, 2 to the 16 minus 1. A double word, 2 to the 32 minus 1. and then a quad word 2 to the power of 64 minus 1. Let's do a demonstration now. We're going to do it in Windows, and then we're going to do it in Linux. And what we're going to do is we're going to define some variables, each one the size, and then we're going to take a look at them in memory. So let's do the Windows, and then we'll do the Linux. All right, let's start our demonstration here, and I've reduced the resolution of my Windows quite a bit here, so my videos can be a little bit smaller in size. So let's go ahead, and we've got Visual Studio up and running. I would suggest that you pause this demonstration until you get yours. Again, it would be a good idea for you to follow along, and let's create our first project. So we're going to create a project. I'm going to go scroll all the way down, and I'm going to grab this assembler. Now, we're going to do a 64-bit application here, so I'm going to select the ASM template 64, or whatever you named it for your 64-bit template, and I'm going to call this ASM 64-bit data sizes. You can call it anything you want. Go ahead and let the project get set up, and after the little wheel finishes turning, we're going to go ahead and take a look at the source code. And let's go ahead and create our first variables. So what we want to do is we want to create a byte. Now, one thing I'm going to do is I'm going to comment this code. I'm going to comment it pretty well. And comments are so important in assembler language. And in both Linux and Windows, a comment starts with a semicolon. So I'm going to say define a single byte. And to do that, under Windows, I'm going to say byte, give it a name. Now in Windows, you can say byte, and I'm going to give it a value. I'm going to create another byte. This time I'm going to use the define byte keyword and make that, let's keep these simple. Let's make this 11 and let's make this 12. It makes it very easy to find those values in memory. So why are there two different things? Well, the byte keyword is really a macro that the Windows Visual Studio debugger uses to decide how to display things. DB is really the assembler keyword, and you can use this in both Linux and Windows. So I actually like to use the DB because it's compatible across all versions or across all of these different operating systems. So that's how we create a byte. How do we create a word? So I'm going to say word variable, define word, and I'm going to make this one 1122. Let's make these hexadecimal because that's going to make it even easier to find. So we put an H at the end of each value, and then that makes it hexadecimal. Let's do a word variable, define double word. So that's a double word variable, and we're going to make that 11223344H. And then let's make a quad word variable. Define quad, and I'm going to make that 1122334455667788. 8 bytes. And remember, a byte is 2 nibbles when you're talking about hexadecimal values, and that's why I do it that way. So I'm going to save that. I'm going to go and click on my no-op. I'm going to say debug, toggle breakpoint, so we can see our breakpoint on line 14, and I'm going to build. Actually, I'm going to clean it first because it's a brand new project. And let's take a look at our output window here. And I'm going to build it. We might get that same problem with retargeting. And it failed. So I'm going to retarget it because it's an older template, perhaps. And then let's build it. And it built just fine. So 1 succeeded, 0 failed. So let's go ahead and debug it. Now, because I put a breakpoint on line 14, when I debug it, start debugging, it's going to stop there, and then we can view our variables. All right, great. Now, the debug window is kind of small because I changed my resolution. Let's see if we can't make that a little bit. So I'm going to click on the source code here. I'm going to close these little windows that I really don't need. And I want to see my source code. This is what happens when you reduce your There we go. So there's my source code. I had to close all those debug windows. All right, so let's take a look at byte variables. So I'm going to highlight the address. Again, I went up to debug Windows memory, and I selected a memory pane. And because I did that in the previous demonstration, it's still there. So let's go ahead and I'm going to type ampersand byte variable. And I'm going to right click, make sure I'm looking at 1 byte integers, hexadecimal display. Again, I right clicked, 1 byte integer hexadecimal display, and we can see our 12 right there, and there's our 12. Now let's go ahead and put an ampersand word variable. There's our word variable. Now it looks backwards. We're going to talk about that little endian order later, but I'm going to right click on that and say 2 byte integer, and there's our 1122, our 1122. Let's take a look at our dword variable. I'm going to right click and say I want to say it as a 4 byte integer, which is what a double word is. And we can see our 11223344, just like in our source code. And on one last one, I'm going to say ampersand quad word variable. Oh, I must have typed that in wrong. So I say quad word variable. Variable. I typed that in wrong down here in my source code. I'm going to right click on this, and I'm going to say 8 byte integer. What did I do wrong here? QUADWORD Huh, that's kind of weird. I can see it right here, 11223344. So there it is right there. It's maybe has something to do with the resolution or whatever, but yeah, that's it right there. That is the... Oh, wait a minute. Did I forget the ampersand? Yep, I think I forgot the ampersand. Yep, that's what it is. I love making mistakes like that. So ampersand quad word VARABIE. There it is. So I forgot that ampersand. That's the kind of mistake you might make. And so there's our 1122, and I made sure I right clicked and selected 8 byte integer. So you can see it right there. Now if you want to see what the decimal value of that big huge number is, I can right click on it and I can say unsigned display, and that's what 11223 is in decimal. Crazy, right? All right, so that is how you define those different sizes of variables and how you look at it in the debugger. Let's go look at the Linux version of this. Hey, and welcome back to our Linux demonstration of different data types. So let's jump into it. So I'm going to go into my documents folder under my home folder, and I'm going to create a new 64-bit application. And I'm going to select the Linux 64-bit template right there, not the functions, but just the normal template. Let's go into that. And we really should rename that. So I'm going to rename it to Linux ASM 64-bit size demo. Let's go inside of that and let's edit our program. And if you watch the Windows one, if you use the DB, the define byte, the define word, the define double word, it's going to look exactly the same on Linux, which is why I like to use those. So I'm going to say byte variable, define byte, 1, 1. I'm going to say word variable, define word, 1, 1, 2, 2. And notice the H at the end, it makes it easier to view those values in the debugger if you use hexadecimal. D word variable, define double, 1, 1, 2, 2, 3, 3, 4, 4. And Q word variable, define quad, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8. And there you go. That's simple. DB for define byte, DW for define word, DD for define double, and DQ for define quad. So I'm going to go ahead and make that. It built just fine. Now I'm going to go back here, open in terminal, and I'm going to type kdbg main. Again, kdbg is my favorite debugger on Linux. So I'm going to scroll down to my first no op, put a little breakpoint right there, and let's run it. All right, so the program has started. The no-op has a little green arrow, so that's where we are. But I'm going to scroll back up to the variables so I can actually remember the variable names. I click on the memory tab. I go up here. I type ampersand byte variable. And we can see this big number here. I'm going to right-click on this and say bytes. And there's my 1, right there. The very first one, 1. I'm going to now type word variable. Right-click and select 2 bytes, and we can see our 1122. That's this guy right here. We can do the same thing on our dword variable. This time I have to right-click and say 4 bytes, and there's our 11223344, just like we did there. And the last one, let's go ahead and put ampersand keyword variable. Right-click on it, say 8 bytes, and there's the 11223344. Crazy, right? Big number. I can also look at this as a unsigned decimal, and that's the same number that we saw in Windows. So there you go. So that's how you define variables. Also, I want you to notice something. I'm going to right-click on this and say bytes. I'm going to go back to the byte variable. Notice how all of our data is right up against each other. That's because when we define data in an assembly language program, we're not really defining data, we're just labeling memory locations. And they're contiguous. They're right after one another. So the 11 is right before the 1122, which is right before the 1122-3344, and so on. So they're contiguously allocated in memory. All right, great demo. Let's continue on, this time with signed variables, because right now all we've done is unsigned. Hey, welcome back. Hope you enjoyed those demonstrations. Hope you were able to keep up. The beauty of YouTube is you can always go back and review those videos and practice and get that skill going. So for right now though, let's move on and let's take a look at signed integers. Now, the CPU uses a really interesting method of representing signed numbers in memory or in a register, and we'll talk about registers very soon. And that's using the most significant bit. That most significant bit, if it's turned on, it's a negative number. If it's turned off, it's a positive number. The problem with that, though, is that you've lost the largest valued bit that you've got in your data area, in your variable, which means you can't have as large as numbers, but you can have negative numbers now. So there's a trade-off. And if you are a C or C++ or Java programmer, you can actually look at the ranges, and signed numbers are much smaller than unsigned numbers. But signed numbers can also have negative, which unsigned cannot. So let's look at some examples of that. So with that said, in a single byte, the 8th bit, 2 to the 7, is not used as a value bit. So the entire signed byte only has 7 bits instead of 8 to represent the value. So it can never be larger. So in a signed number, if the most significant bit has a value of 1, as I said earlier, the number is negative. If it has a value of 0, the number is positive. So as an example, since the leftmost bit is 1, it must be a negative number in this case. If the most significant bit, the farthest left byte or bit in the byte, is a 0, it must be a positive number. So since we only have 7 bits for a byte, the largest possible value is 2 to the 7th instead of 2 to the 8th, 2 to the 7th minus 1, or 127. The smallest negative value can be a negative 2 to the 7th or minus 128. In a word, the largest number is 2 to the 15th instead of 2 to the 16th, 2 to the 15th minus 1, or 32k, or 32,767. Actually, I believe that's 32k minus 1. And then the smallest negative is 2 to the 15th negated, or 32,768 negative. A double word, minus 2 billion, plus 2 billion. A quad word, what is that? That's hundreds of thousands, million, billions, trillion, quadrillion. Is that sectillion? A positive 9 followed by all those other numbers, or a negative 9 followed by all those numbers. So let's take a look at what signed numbers look like in memory, both in Windows and in Linux. Hey, welcome back. This time what we're going to do is we're going to take the same program we did in Windows in our first demonstration on Windows, and we're going to add some signed variables. Now, I always like, when I create signed variables in my assembly language programs, I always like to put an S in front or an S in back to remind me that that variable is supposed to be signed. Now remember, and maybe I didn't say this, and maybe, so now's the time to say it, is the CPU doesn't know the difference between signed and unsigned. It's just a bunch of bits. You, as the programmer, have to keep track. So by putting an S, it might help you, and that's a little trick that I've used. The other thing that we didn't do in this example is we didn't really put all of our comments. So it's always a good idea to put your comments. Now it might seem kind of crazy that we're going to be putting a comment for each variable. The important thing to remember is make your variable names self-defining. So instead of X, make it sales amount, or instead of Y, make it tax rate. Make it a very good variable name. So let's go ahead and create some sign. So I'm going to first create a signed byte. So I'm going to say signed byte variable. And I could have said sbyte, that's that Windows macro, but I'm just going to say define byte because it doesn't matter. The CPU is going to see it just as 8 bits. And I'm going to make it a negative 125. And I'm going to do this in decimal this time because in hex you really can't specify a negative hexadecimal value. You have to convert it to hexadecimal, take the 2's complement, which is going to be the next video after our sizes, after our data variable video. I'm going to make a signed word, define word, and I'm going to make this minus, I don't know, 2,567. I'm going to make a signed D word variable, define double, minus 32,678, I don't know. And then let's do a signed keyword variable, define quad, minus, let's just put a bunch of numbers there. And let's take a look at what those look like. So let's build our program. Let's double check the output to make sure we didn't have any problems. Yep, 1 succeeded, 0 failed. Let's go ahead and now run this. Now remember, I did put a breakpoint on my first no op, so I don't have to worry about it. It's going to stop right there. So let's say debug, start debugging. And we're going to scroll up. There's our variables. And I'm going to select ampersand sbyte variable. And I'm going to right click, make sure I'm on 1 bytes, and there it is, 83. So 83 is associated with negative 125. Now, unfortunately, on Visual Studio, you can't look at them as binary. I don't know why they did that, but you can't. You actually can't look at it as binary. So we're not going to get as much value out of this demonstration as we will the Linux demonstration, because you can look at it as binary. So with that said, you know how to look at variables, you know how to create them on Windows. Let's jump over to the Linux demo so we can actually see the binary values of those variables. All right, welcome back. This time we're going to take a look at signed variables in Linux. And as I said earlier, the Linux debugger lets me look at things, or lets us look at things as binary, so we can actually see what those binary values, signed values are. So I ended my debugger right there, and I'm going to go back into my source code, and I'm going to create some more variables. Now, this time what I'm going to do, just to show you how useful, I'm going to go ahead and paste those variables and put an S in front of them, so I know they're signed, and let's put some values. Minus 23, minus 126, oops, minus, give it some pretty large number there, and minus, let's give this a crazy large number. Okay. Now, as I said earlier, or in the Windows demo, I'm going to do these as decimal because it's much easier to define negative numbers in decimal than it is hexadecimal. Now, instead of building it in Genie, I'm going to go back to my window here where we started the debugger, and I'm just going to type make. And make, that's basically what Genie did, right? It just executed the make file. And now let's debug it. So let's take a look at our binary values, signed binary values. Let's make sure our no-op is breakpointed, and let's start it. And I always like to scroll up so I can see my variable names. All right, so let's take a look at ampersand signed byte variable. And there's my signed byte variable. I'm going to right-click on that. I'm going to pick byte, make sure it's on byte, and then I'm going to click on binary. And there you go. So you can see 111.01001. That is negative 23. Notice the 1 in the most significant bit. That means that it's negative. Now you might say, well, wait a minute. 1101001 is not 23. What in the heck's going on here? Well, we haven't talked about it yet. That'll be the next video, but that's what we call 2's complement. 2's complement is a way for the CPU to be more efficient when it stores data out in memory, and it just does it in reverse order. So we'll see that. Now, I'm sorry, that's the little endian. It'll actually save it in 2's complement, which we'll see in the next video. So let's take a look at our word variable, our signed word variable. There's our signed word variable. I'm going to right click and select 2 bytes. And again, it's negative with a 1 on the most significant bit. And all these other 1s and 0s, that's stored in 2's complement, which, as I said, will be in the next video. So that's the demonstration on Linux. You can see that I proved my point is that the most significant bit is 1. If it's negative, what if it's positive? What if it's unsigned? The most significant, actually, what am I looking at here? 1122. Oh, that's right, because it's in hexadecimal. So if I right click on this and click binary, you can see that 1122 actually has a 0 on the most significant bit. Let's make sure that that's 2 bytes. There it is. So that is a positive, and all this together equals 1122 in hex. Okay, so I hope you enjoyed that. We talked about different data sizes. We talked about signed integers. We talked about unsigned integers. And what we're going to do next is talk about that pesky 2's complement thing that I mentioned earlier as to how variables are actually stored in memory. It's not going to be a super long video. It's not going to be a whole lot of demonstration, but we are going to talk about the simple procedure of what the computer actually does to store signed values in 2's complement. See you there.